So, pleasant afternoon to everybody. I am Sarthak Narkedipilli and I am a fourth year undergrad student from IIIT Dharwad and I am pursuing my majors in computer science. So, these are my co-authors and we have been mentored by Dr. Pawan Kumar. Sorry, I haven't added his name yet. So this is a topic, FLDECO-BC, a privacy and provenance preserving, provably secure, a federated learning framework for vehicular ad-hoc networks. So this would be the presentation overview, introduction, preliminaries, assumptions, workflow of the proposed framework, key features and the security features, the sort of security and attack comparison with the other existing frameworks, band logic analysis, and the possible applications that we could incorporate this particular framework into to make this much more viable, much more better in the existing studies. So this is the introduction. So the problem statement that we had looked for was as and when the vehicular ad hoc networks grow in number, so there is a huge increase in data exchange and data generation. So this data have to be properly utilized and analyzed to make sure that the applications associated with it would be, you could support the network with the applications by training this particular data. So we would like to perform a more secure, more privacy-oriented, collaborative learning to support the vehicular ad hoc networks. So, in short, the problem statement is to keep the data transmission, the raw data transmission, and the collaborative model manipulation in a much more secure way. So that is what we are proposing in this particular framework. So these are the vulnerabilities that we would like to address by proposing this particular framework. So I would quickly like to run through the preliminaries. So firstly, the vehicular ad hoc network. So the basic, it's like a decentralized network. So we have assumed this particular vehicular ad hoc network onto a P2P network with sufficient infrastructures like RSU, the roadside units, the OBUs, the onboard units, etc. with V2V and V2I communications, and very generically speaking about the V2X communication as well. Then the main aspect, the mother or the backbone of this framework would include decentralized oracles. So these decentralized oracles are like the gateway. Like we all know, the blockchain systems are isolated systems. So it bridges between the real world data. I mean, the data that is collected from the vehicular ad hoc networks rather from the sensors, etc. So it bridges between the blockchain and the data collection. So that is decentralized oracles. So very briefly speaking, so there's oracles. They come to a general consensus to accept whether a particular data is viable, which is worthy to store in a particular network or not. So federated learning is the buzzing word in the current world, in the current days. So federated learning is basically training your model in a more collaborative or a more decentralized fashion, as in in very short, your data can be, you can have different people having various bits and pieces of data, and all of that data could be trained without them actually putting it onto a centralized server. That is federated learning. And blockchain, of course, it is distributed immutable digital ledger, and this particular term would require no formal introduction. And then the cryptographic primitives that we have used is zero knowledge proofs. So zero knowledge proofs is cryptographically proving that you possess some amount of information without actually revealing it. And secure multi-party computation. So this is to offload computation. So you could compute a particular function with different inputs with different nodes without you actually revealing your particular input. That is secure multi-party computation. And Yeah, and all of this is going to be used in the particular framework that we have proposed. And before I would like to discuss about what we are proposing, I would like to also very keenly throw light on the assumptions that we have made. So firstly, the data quality and the resource constraints. We assume that at least in the edge side has decent amount of edge fog support to at least train the local models, and then you could transmit those weights. And then it is also assumed that there's sufficient amount of computational resource such that there's the cryptographical jargons that we have specified earlier could be applied onto it. Then verification and trust assumptions. So it is assumed that the blockchain is compliant of verifying the proofs that are generated, like it could be Polygon, for example. So it uses of ZKPs, it utilizes ZKPs to verify it on blockchain. And limitation of malicious actors. So since we are using the consensus mechanisms associated with blockchain and the decentralized oracles, so we assume that there are more of reputed actors and a very less chunk of malicious actors. So this is essentially to rule out the cases like the 51% attack, wherein the entire network is hijacked, or the 1/3 rule of the Byzantine fault tolerance mechanisms. And yeah, so now the part. So I believe I have set the stage for describing my particular workflow of the proposed framework. So the step 1 would include local model training. The OBUs and the RSUs collect relevant data and train it on the local machines without sharing the raw data. Then the stage 2 includes secure weight storage. The trained model weights are encrypted and then transferred to blockchain via decentralized oracles to maintain data privacy. So essentially what we are doing is that despite the blockchain gives you the transparency, the pipeline of the federated learning training is happening via the blockchain and the decentralized oracles to ensure that there is no not falsified data or any malicious acts or malicious manipulation of the model weights happening. And the step 3, so whatever model, the local weights were there on the blockchain, so they are essentially taken by different nodes, since we all know blockchain is a peer-to-peer network, and the network is comprising of various nodes. So these local weights are aggregated using these other computational nodes, and using an SMPC, and there are ZKPs also generated to validate the computational correctness of these particular nodes. Then, of course, the verification and the blockchain storage. So initially the local models are globally aggregated to compute a global model, and cryptographical proofs are generated against it to validate its correctness. And now it's the verification part. Anybody, any miner or any actor in the particular blockchain could anytime go back and look at the past log and verify the particular the correctness of what has been computed earlier. So this is the pictographical flowchart of what we have done. So of what we have proposed rather. So I'll just walk you through in a jiffy. So OBUs and the RSUs collect data, and the local model is being trained, and then the encryption of the local weights is being made. So before you upload it into the blockchain. So what happens is that before this particular step, so you pass it through consensus or a decentralized, you pass it through decentralized oracles, and then you rather encrypt it and then you store it on blockchain. Then you would use secure, and this is the local weights. You have got the local weights in the blockchain, and so you would compute the global weight via secure multi-party computation, and then you generate the proofs associated with it, and then you broadcast those particular weights to the various vehicular nodes for their set of analysis of their set of applications. And then, yeah, and then you utilize the model, and then you verify, and then you utilize the model at the local level. After the global weights is being broadcasted to the each individual vehicular nodes. So the key features include privacy preserving training. So at any stage, your data does not leave your edge device. So your data is intact, and the entire flow, the entire pipeline of the training is being steel solidly crafted with the cryptographical jargons proposed. And it is attack resilient, and it is resilient to attacks like civil attack, replay, and man-in-the-middle attacks. And it's because of the features offered by blockchain and the decentralized oracles. And this is scalable in terms of like the general consensus or the very raw or the vanilla blockchain if you have to use. It's better compared to that. And this could also be made better by utilizing microservices, like that could be deployed easier. And then efficient model sharing. And since blockchain offers secured networking, secured communication, and your model, the entire pipeline is rock solid, it cannot be broken. And these are the security features that we have very specifically highlighted upon. One is the anonymity, then it is non-traceability and impersonation attacks, message modification attacks, replay and man-in-the-middle attacks. So I would like to throw some light on impersonation attacks. So this could be combated by authentication that decentralized oracles provide. So any random actor cannot just plug in himself or inject falsified information or falsified weights, manipulating the weight manipulation. So all of that has been all the vulnerabilities have been kept in check with the framework that we have proposed. And this is from the literature survey that we have done. I mean, this is a very subjective literature survey that we have done. So these are the list of attacks, and these are the frameworks from the literature survey, and this is the proposed framework. So this is a very subjective way of telling that our framework is resilient to a lot of the attacks. And yeah, and moving on, we have also proposed the mathematical correctness of this particular framework using band logic. So band logic is essentially a formal method for analyzing security protocols, particularly having authentication and communication by examining the beliefs of the involved entities to identify potential weaknesses through its non-applicable steps without message exchanges. So in the four-step proposed framework, of which 1 and 4 is not, you can't actually apply band logic upon it. So wherever there's more of this message authentication, that is the place where you could apply band logic essentially. So this is the band logic for step 2 and step 3. So step 1 and 2, you can't apply band logic to it. So this is the jargon. You can have a look. And yeah. And the possible applications of this particular framework would be traffic management, accident prediction, and collaborative route optimization. So, I mean, that's the thing. I mean, this offers, you could, the data is abundant. So you could take a lot of the data and you could help it support the network and provide more applications to it, and that would help in the user experience, and also keep ourselves a step ahead in the future. Thank you.